Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are now on lecture 14. We are discussing about contact mechanics of loading of an axisymmetric loading of an elastic half space, and that is without adhesion. So, in the last few lectures I have gone through these different type of load distributions. P is equal to P 0, which is the uniform load, and here this is P is equal to P 0 into 1 minus t square by a square minus square root, and here it is plus square root like that, and in each case we have obtained the vertical displacement or deformation at z is equal to 0 within the contact area and outside the contact area, and we have also obtained the, or at least described how to obtain the horizontal displacement, okay, at a point that is within the contact area and outside the contact area, and these tables or equations we have discussed in the last few lectures. So, today I will like to cover a new topic, that is loading on a triangular area of contact, and we will consider uniform load, but before that I will just like to solve few problems and then we will start discussing that. So, here the problem is that a circular area of radius a on the surface of an elastic half space is subjected to compressive load with pressure distribution P is equal to P 0 into 1 minus t by a, that is the linear variation. Obtain the vertical displacement at the center of the area of contact and at the periphery. So, we can use the same kind of derivation or knowledge that we have discussed in the last class. So, for example, the V, the vertical displacement at this particular point B, because of this infinitesimal loading at this particular infinitesimal area at this particular point, that will be given as 1 minus sigma square pi e, and this particular quantity P s phi s ds s d phi into ds, and there is a divided by s here, this s has been cancelled here. So, here like that. So, this we have discussed, and here this P is actually written as P 0 into 1 minus t by a. So, the t is this distance, that is the distance from this point and this particular point C, and so t has to be expressed in terms of s is from 0 point to this point, that is s over here. So, the coordinate of s with respect to b, the coordinate of c with respect to b is actually s phi over here. Okay. So, that is what we are doing, and so t can be expressed as this expression, and so it is actually like this. So, this we have discussed with respect to the other loads, and here this S1, that is 0 to S1. So, S1 is this particular point. So, here the solution of S1 is comes from this equation, and it is something like this. So, this is all we have discussed, and that is the results that we can use for solving this particular problem. This is just to estimate, just to demonstrate that whatever we have discussed so far, that can be useful for solving many other kinds of problems. So, for example, here this is a linear loading problem. Only thing is that the math may not be all that simple. Many cases there is no analytical solution, one has to find a numerical solution or like series solution like that elliptic integrals or like that, but otherwise the conceptually, okay, we can actually address this kind of problems. So, here for example, this V will be written something like this, and this can be further written over here. This limits from 0 to 2 pi, and this is limits from 0 to S1 here, and if I integrate it, so it will be S1 d phi and this particular integral. So, now we can go on deriving this and we can do this integration and we can get the expressions, but since we have a simpler problem here that we at a specific point we have to find out this the vertical displacements. So, we will just take advantage of this problem. So, we will find it out what will be this integral at r is equal to 0 here. Okay. So, it is otherwise this is a problem of just algebra, nothing more. 1 minus sigma square by pi e here, and this is P 0, and this is S1 d phi. So, S1 is 0 to 2 pi, and S1 is given as minus r cos phi plus this is r square cos square phi plus a square minus r square, this is square root. So, 1 by 2 here, yeah. then this is d phi here, and minus this is d phi here, this is d phi, this is d phi here, yeah, this is d phi here, then minus 1 by a, and here this is 0 to 2 pi and 0 to s1, and over here, okay, we can simplify this by writing r is equal to 0 and r is equal to right, so it will be s square here, so the s comes out over here. So, it will be s ds and d phi, and then finally, we can write s ds as s square by 2, s1 square by 2 or like that, and we can further simplify this putting r is equal to 0, what I have done over here. So, it is s1 d phi over here, s1 is given like this, and here r is equal to 0. So, if r is equal to 0, r is equal to 0, r is equal to 0 here. So, therefore, this is a, it comes out to be a here like that. So, here we get a, so this is a here, and then we are integrating from 0 to 2 pi. So, I will get here actually 2 pi, okay, 2 pi over here, and from here also I will get here also I will get half of a by 2 here. So, actually from combining these two, I will get here a by 2 into 2 pi, and finally, I will have this particular expression over here. So, that is basically the answer for this particular problem. So, it is gets simplified because we are trying to find out the deformation at a specific point, that is r is equal to 0. So, we can simplify this integral, otherwise this is little more cumbersome algebraically. Similarly, at r is equal to a, if I want to find out, so we have to substitute r is equal to a for all these cases, and here r s1 comes out to be actually 0. So, therefore, this particular quantity will come out to be equal to 0. So, remember that the load is 0 at the periphery. So, here also it comes out to be 0. So, it is like that. So, we can basically to demonstrate that given any kind of load distribution, we can find out the displacement or deformation vertical or horizontal at the surface. So, here is another example. This is also based on principle of superposition. So, similar problems we have discussed earlier. So, let us say the pressure distribution given by here like this, and this is the distribution in all these 3 different circular area the load is being applied, and what is the deformation at this particular point C, that is what we want to find out. So, that is the problem here. So, here remember that this particular problem that sits at the periphery of this circle 2 and the circle 3, and it sits outside the peripheral area of contact for circle 1. So, we have to use the equations or expressions accordingly. So, here for example, because of point area 2 and 3, the deformation at this particular point C, okay, has to be multiplied 2 here, because both the cases it is vertically down. So, it is 2 here, 2 into 1 minus sigma square by E by P by 2a. So, that is the result that we have derived earlier for vertical deformation at the periphery. Now, for this particular load distribution, the vertical deformation is constant, okay, everywhere. This is the load distribution for a flat plate punch, right, that we have discussed. So, here, so this is 2 into 2 here. So, basically this is the vertical deformation that we will get at this particular point because of the area loaded on these circles is 2 and 3. So, it comes out to be like that. And for 1, we need to use the slightly different expression, which given by in terms of sine inverse function. So, here 2 into 1 minus sigma square by E P 0 into a sine inverse a by r. So, this also we have derived in the last few lectures. So, again here what is the value of r? Now, r can be easily seen as square root of 3a, because we have a distance between this point to this point, okay, this is 2a from this is basically 2a, this is 2a. So, it is 2a into sine 60 degree. So, this is 60 degree here, and so therefore, it is sine root 3 by 2. So, it is square root of 3a. So, r is equal to square root of 3a, that is what we have substituted here, and finally, by putting all the numbers and adding and all that, we get this particular result or answer. Please check if you get the same thing or not. So, that is all about this symmetric loading. Now, we will go for a slightly different kind of loading area. So, this is a triangular area of contact, and I will explain it to why I am interested in triangular area of contact. So, this is uniform compressive loading, it can be some other type of distribution as well, but this is uniform loading is simple to discuss and handle. So, therefore, we are doing that. What are the vertical and horizontal deformations at point O, let us say. So, remember that this is a right angle triangle. So, we can find out the vertical displacement over here again by this principle of superposition, and for that let us say that there is a small area at this particular point C. So, what you need to do is to draw this line that connecting from this point to C. So, like that. So, let us say this angle is phi and this angle is d phi, this small change in angle, this is d phi, and so this distance is let us say ds, and this distance from here to here, this is let us say s here, like that. So, the area of this infinitesimal area, that is s d phi into ds, that is the area that we get over here. So, what is the vertical displacement over here because of the loading on this infinitesimal area that we can write down. So, that we can write down, remember that will be v at z is equal to 0, and that is given here like this, dv is 1 minus sigma by 2 pi. Remember that this displacement can be deformation can be written either in terms of Young's modulus or in terms of shear modulus. And if it is Young's modulus, okay, this will be mu will be written as 2 into 1 plus sigma. So, it will be written as E over 2 by 1 plus sigma. Okay. So, mu can be substituted by 2 by 1 plus sigma. So, it will come out to be 1 minus sigma square by 2 pi E into s, and into this p of s and phi here, and this is s ds s ds into d phi here. So, this s and this s will get cancelled. So, we will have the other terms. So, we can actually write that and we can integrate it. So, that is what I am going to do here. Remember here that this s varies from 0 to s1. So, that we need to write down how to write, and this angle, this particular angle theta, this is d phi here, and this is the whole angle theta. So, sin theta is equal to rather tan theta, right, sorry, tan theta I will write. So, tan theta will be a by b. So, tan theta is a by b over here, and so theta phi varies from 0 to theta, right, phi varies from 0 to theta like this. Now, so s1 we have to write, right. So, p s of this is p s is constant. So, this is actually p 0 over here, and so yes. Now, s1 will be equal to b sec phi, because this is b here, and so s1 cos phi will be equal to b. So, therefore, s1 is equal to b of sec phi, right, b of sec phi over here. So, that is the limit for s, and the phi goes from 0 to theta, that I have already talked. This is tan inverse a by b. So, therefore, we have the ds into d phi over here, because p 0 goes outside. So, here ds, okay, that is integrated from 0 to s1. So, s1 is this, therefore, I get a b sec phi d phi. So, the sec phi d phi, that integration is ln of this quantity over here. So, once you substitute this, okay, here sec 0 will be equal to 1, and tan 0 is equal to 0, right. So, therefore, I get over here ln of this quantity, okay, b of ln b into ln of sec theta plus tan theta, where tan theta is equal to a by b, and so therefore, this quantity vi, the integration value will be b, and ln of sec theta is 1 by cos theta, 1 by cos theta will be here, from here it will be b divided by square root of a square plus b square. Okay, so, cos theta will be b by square root of s plus b square. So, therefore, it will be like this, plus tan theta will be a by b, right, like this. So, that will be the expression, that will be the results over here, and so here it will come out to be like this, 1 minus sigma by 2 pi mu, as I said that mu can also be written in terms of Young's modulus, p 0 into b, and ln of a by b, and over here it will be 1 plus a square by square root 1 plus a square by b square. So, this is the simple result. that at the point at point O, okay, what is the vertical deformation, that is given by that expression that we have just derived over here. Similarly, let us say we want to derive the horizontal deformation at this particular point O. Remember that because of this loading over here, the horizontal deformation will be in the radial direction. So, it will be radial direction in this direction, and it will have both cos component and the sin component. So, that is what I have written here, cos phi and the sin phi, both of these components have to be calculated and can be calculated. Okay. So, I have not derived the whole thing, but you are interested, you can derive it, and we can do that. But this is the expression by which one needs to derive those quantities. So, here S has to be written in terms of cos phi, sec phi, and then is cos phi, we can derive it actually. Now, let us say that the vertical deformation at point C, which is outside the area of loading, that needs to be found out. So, here the loading has been done within this shaded area, and we want to find out that what is the vertical displacement at this particular point, okay, C, which is at a distance r from this point O over here. So, we will use essentially the results that we have derived in the last derivation. So, here what we will do is something like this, which is quite interesting. So, here let us say I join this point C to B, C to B over here, let me extend it over here, let me draw a line perpendicular here. So, this angle is perpendicular. So, I have C, O, B, and I guess this point is D over here, and so let us say that this angle I write it as alpha, this angle is alpha. So, I have here actually one right angle triangle I have formed, which is CDO, and then I have got another right angle triangle CDB over here. So, I have in a sense what I have done is that I have actually we have made two additional right angle triangles, okay. And so, the deformation at this particular point, because of the loading over here, okay, again by principle of superposition I will find out. So, for example, it will be something like this. So, let us say the triangle CAB, okay, loading because of triangle CAB plus triangle CDO. So, in this CAB is basically this triangle over here, this triangle over here. So, what is the loading? Because of the loading over here, what is the vertical deformation here? Plus I have added this part, this particular portion, so that is CDO. So, now there is an additional area that I have added is this, that is CDB, that needs to be subtracted. So, minus CDB. So, the loading on this area triangle CAB, that needs to be because of the loading there, what is the vertical deformation at C, that needs to be found out, and then the loading because of loading on area CDO, that is this additional triangle that I have just drawn, that needs to be found out, and what needs to be subtracted is because CDB, that is this particular portion, that additional area that I have added, okay, here in these two cases. So, that needs to be subtracted. So, if we do that, then we will have the vertical deformation at this point C because of the loading on this area, this shaded area like that. So, in order to do that, we need to just find out few different lengths and angles. For example, this angle alpha. So, over here this is a similarity triangle actually, CDO is right angle. So, here this CDO, yeah, OAB is also right angle. So, this angle and this angle are same, this is actually theta. So, this alpha is actually pi by 2 minus theta. So, this angle alpha is actually this angle alpha. So, these two angles are same. So, therefore, tan theta, tan alpha will be B by A, tan alpha will be here B by tan alpha B by A. So, here the tan alpha is basically given by this length. Now, we need to find out for CAB. So, CAB we need to find out CA and AB. For CDO we need to find out CD and OD, and for triangle CDB we need to find out these two lines CD and BD, that is all you need to find out. So, see CA, So, C A is easy. So, C A is equal to, this is R plus B, this is R plus B, and A B I already know. C D, so the C D will be equal to, this is R cos alpha, because this is R and this is cos alpha, this will be C D cos R cos alpha, and then I have O D. So, the O D is R sin alpha, O D is equal to R sin alpha. Then I have C D. So, C D I have already found out, C D I have already found out, and B D I have to find out. So, B D. So, B D is this length, that is D O plus B O. So, that is D O plus B O. So, what is D O? D or O D, that I have written here, R sin alpha plus B O. So, B O is square root of A square plus B square, B O, yeah, square root of A square plus B square, A square plus B square. Now, this sin alpha cos alpha, that can also be written in terms of A and B, because we already have this tan alpha is equal to B by A. So, it is not so difficult. So, here let us say R will be equal to sin alpha will be B by square root of A square plus B square, plus here B O is square root of A square plus B square here. So, it is like this. So, it is doable, B D is like that, and then R cos alpha will be equal to R and cos alpha, that is A by square root of A square plus B square, like this. So, once we have that, then it is just matter of taking care of few things. So, I have already derived this quantity, I do not need to worry about it. So, here for example, that this is the result that we had derived, this result I have derived. So, here this A and B are to be replaced suitably. So, for example, like if I talk about C A B, here A remains same, but B has to be replaced by B plus R. Okay. So, therefore, V, let me see this quantity, that is already there written. So, this will be equal to 1 minus sigma by 2 pi mu, this is P 0, B has to be replaced by B plus R. So, B plus R here, and ln of this will be A by B plus R plus, here it is square root 1 plus, this is A square divided by B plus R whole square. So, for vertical displacement at C, because of the loading in the area C A B, that will be given by this expression. Similarly, the vertical loading at let us say C D, so I have written already C D O. So, the C D O when you find out, so A has to be A has to be replaced by O D. So, right, A has to be replaced by O D over here, because this is the rectangle 90 degree here, this is also 90 degree here. So, A has to be replaced by O D and B has to be replaced by C D. So, these quantities I have already found out. So, therefore, this will be equal to 1 minus sigma 2 pi mu B 0, here B will be replaced by C D. So, C D I have already obtained, C D is R cos alpha. So, this is R and cos alpha. So, cos alpha I have already written here, cos alpha will be A by square root of A square plus B square, cos alpha will be A by square root of A square plus B square, that is cos alpha. Now, this is done. Okay. Then ln of A by B. So, A is replaced by O D. So, O D is R sin alpha and it is R sin alpha, and B is replaced by B to C D. So, C D is R cos alpha. So, sin alpha by cos alpha, that is tan alpha, and tan alpha is B by A. So, it is B by A, because this angle is alpha here. So, this is B by A, and then plus it is square root of, so A 1 plus, and this is, it will be B by A again, because that is the way it is, it will be turned out to be B by A whole square. So, yeah, so like that B by A, right 2 P 0. So, B is replaced by C D here. So, therefore, this is here R of C D here, R of cos alpha is given like this, right. So, here it is like this, right, and then we have let us say for C D B. So, C D B here, for C D B, B has to be replaced by C D and B has to be replaced by C D, B has to be replaced by D, and A has to be replaced by B D, A has to be replaced by B D here. So, that also we have found out earlier. So, this is turns out to be like this. So, once you substitute for that, we can easily get here. So, instead of B, B has to be C D. So, B we have here R A square root of A square plus B square. So, that is this quantity, because B is being replaced by C D and then A is being replaced by B D. So, the B D is this quantity. So, A by B has to be found out. So, it is little more involved algebra, but it can be done. So, I have already done it. So, it is something like this. So, this is the way we can actually find out that if the point lies outside the contact area, okay, what will be the total deformation. So, which is now written here. So, this is plus here and this is minus. Okay. So, the way that I just discussed, so one can actually easily follow. So, this will be the answer for vertical deformation at point C because of this loading. So, now let us take a special case in which let us say A is equal to B. Okay. So, it is easy, A by B is 1 here, A by B is 1 here, 1 plus 1 is 2 square root of 2. So, finally, ln here comes out to be ln of 1 plus square root of 2 is comes out to be 0.8814. So, it comes out to be like this. So, yeah, so it is vertical deformation at point O can be easily found out by writing A is equal to B, let us say. Let us say that we want to find out at a point R, R is equal to B is equal to A. So, which is at the same distance as B, and so again R will be equal to B. So, in this equation that we have just derived, just substitute here R is equal to A B. So, 1 minus sigma 2 pi mu, this is P 0 here and this is B plus B, that is 2B here, and this is ln of it is B by 2B, this is 1 by 2 here plus this is 1 plus A by B plus B 2B, that is A square by 2. So, it is 1 by 2 1 by 4. So, this is 1 by 2 1 by 4 here, right, 1 by 4 here, okay, plus this is here A square by 2B square, so 1 by square root of 2 here, okay, ln of this is 1 plus this is again 1 plus 1 by this is 1 actually. So, it is 1 minus R is equal to A. So, the A square plus square 2 A square. So, this is actually A by, it should be A here. So, this is A here. So, A is equal to B. So, it is B here, it should be B here written, again B here, this is square root of 2 here, okay, ln here, and you can write the other quantities, okay, and we can write the derive the whole thing about anyway. So, here like that, and finally, one can get here like this. So, it is just the numbers that had to be put, and one will finally one get this particular result. So, that is the way one can actually get. Now, let us say that vertical deformation at point O, okay, for this rectangular area of contact. Okay. So, look here, we can actually divide this into 4 I think 8 actually I should did it like this, sorry about that. So, we need to we can actually divide this whole area into 8 such triangles, so like this 8 such triangles. So, this is one such triangle, this is another one, this is another one, like that. In each case this points lies at this particular so this point we can, so this is at the same point, equivalent point, okay. This is a square, therefore it is advantage. So, it is a square here. So, basically there are 8 triangles. So, we need to find out 8 into the vertical deformation that will be there because of one of these triangles, and one can actually find out that, and so it is 8 triangles of length b by 2, and so therefore it will be like this. So, it has already been discussed. So, at for A is equal to B, we get this result, and so here B should be replaced by B by 2 here, and therefore we have this particular result. So, that is the result. So, these are the things we can do, and So, today I will stop here, and in the next lecture I will like to discuss little bit more about this point, that why this triangular area is useful, and then we will discuss another interesting point about contact mechanics, and then we will start discussing about adhesion as well. Thank you very much for your kind attention.